A Mealy machine is a finite state machine where the outputs of the circuit are asynchronous. That is, the output or outputs are defined by both the current state and the value of any input variables. This means that as soon as one or more input variables change, the output has the ability to change immediately and not necessarily when the clock ticks. In this video, we'll learn about Mealy machines by considering two different examples. Then, we'll compare and contrast Mealy and Moore machines. In this first example, we'll model a circuit that detects the number 3 from a 2-bit input XY. When any other input is present, the circuit will stay in the reset state. After 3 is present on the input, the circuit will enter the second state and stay there unless the flip-flops are asynchronously cleared by an external signal. The output will be an active low variable called t. This active low variable will be used to trigger an approximately 1 second long pulse on a 555 timer in monostable mode to light up an LED. We will utilize this function of a 555 timer in the sequence detector lab. First, we have to define all of our states. Let's call our reset state A. This is the state the circuit is in when the value of 3 has not been detected. This is not an arbitrary designation for the reset state. This state is, quite literally, the state that the circuit should reset into because the number 3 hasn't been detected when a circuit is booted up for the first time. The state the circuit enters into once 3 is detected, we can call B. We can draw a state diagram for this circuit. Inside each circle is the state name. Now our transitions have a line. Above the line is the input value or values. Below the line are the output value or values for that particular transition. In state A, we will remain in state A if the input is 0, 1, or 2. The value of t for those conditions will be 1. In state A, we will transition to state B if the input is 3. The value of t for that condition will be 0. Any input we receive in state B will continue to keep us in state B with an output value t equal to 1. I will include an additional arrow into A. This shows that an active low reset signal can be used to asynchronously put our circuit into the reset state. This signal will not show up in our state or transition table, but should be used as a reminder to wire up the asynchronous clear pins to an active low signal. Our state diagram is fully defined because every input value, there are 4 because we have a 2-bit input, has a clearly defined transition on the state diagram, and each of those transitions has a defined output value. There are no input conditions that would lead to an unknown outcome. We now derive a state table. We have a current state column containing all of the possible states of the circuit. There are 4 next state columns in this example, as the input values x, y can take on one of 4 values. Note that the next state columns are ordered in gray code to make things easier to place into a K-map. If the current state is A, and xy is either equal to 0, 0, 0, 1, or 1, 0, the next state will be A. If the current state is A, and xy equals 1, 1, the next state is B. Anytime we are in state B, the next state is also B, regardless of the input variables. Then, for each transition, consider the output value. There are now 4 output value columns because this is a Mealy machine and the output is a function of the input. If the current state is A and xy is either equal to 0, 0, 0, 1, or 1, 0, then t equals 1. If the current state is A and xy equals 1, 1, then t equals 0. Anytime we are in state B, the output t equals 1, regardless of the input variables. Now we can select a flip-flop type and assign state assignments. Let's use a JK flip-flop for this example. Each binary state assignment in this example will have 1 bit because that's how many bits are required to distinguish between 2 different states. This means our design will require only 1 flip-flop. Because we selected A as the reset state, that state assignment will be 0. B will have an assignment of 1. Now we can derive the transition table. The current state column will now contain the values 0 and 1, which are the 2 possible values that the output of the flip-flop can be. The 0 row on the transition table corresponds to state A. When we're in A and xy equals 0, 0, 0, 1, or 1, 0, the next state is A, and that's represented by 0. When we're in A and xy equals 1, 1, the next state is B, and that's represented by 1. The 1 row on the transition table corresponds to state B. Regardless of the input value, we'll stay in state B, represented by 1. Then, use the transitions for JK flip-flops to derive the flip-flop values required to create each of these transitions. Finally, fill in each of the corresponding output values for each transition. Now we can take each of the flip-flop value columns to derive next state expressions. These will be the J and K input values for the flip-flop. Put each of the JA values into a K-map and find that JA equals XY. Notice that KA is always equal to either 0 or don't care, which means we can say that KA equals 0 and connect that pin directly to ground. Then we need to derive the output expression for T. T equals X prime plus Y prime plus A. How do we wire this up? Connect the flip-flop to a clock source. Connect the asynchronous clear pin to an active low push button. Connect a dip switch or other similar input device to represent the input variables X and Y. Then, using X and Y, the values from the dip switch, and A, the output value of the flip-flop, wire the flip-flop input, then wire the output function. I wired this up using the 74112 JK flip-flop chip, a dip switch for XY, and a function generator running about 1.5 Hz for the clock. A push button was used to asynchronously clear the flip-flop and put the circuit into the reset state. I can confirm that the circuit follows the state diagram as expected. This specific example is a great use case for a Mealy machine because the trigger input for a 555 timer in monostable mode should be asynchronous, as any low signal on the trigger pin causes the output to be high. This means that long trigger signals can affect the duration of the LED being on. Because the value of T in this circuit is asynchronous, I don't have to worry about the value of T being asserted low for longer than it takes for the clock to tick, keeping the trigger pulse short enough not to cause the output to act unexpectedly. If you'd like more practice, try designing this with a different type of flip-flop, or by selecting a different input variable to trigger a switch to state B. If you want to simulate it, use Tinkercad, as Circuitverse doesn't have a 555 timer. This second example calculates the sum and carry of two 1-bit numbers, such that two 4-bit words can be summed together serially, 1 bit at a time. The high-level schematic shows the different components. A dip switch is used to enter each 4-bit number. Pressing a button will load those values into two 4-bit parallel in, parallel out registers. Then, a separate push button can be used to sum each individual LSB in the register while simultaneously shifting data from the MSB to the LSB in the register, such that the next bit in line is available to sum on the next clock trigger. The finite state machine comes into play as the state assignment is equal to the carryout value. The asynchronous output is equal to the sum, which uses a 3-bit XOR to find the sum of the two values stored in the register added to the carryout from the previous addition step. In this manner, a single full adder can be used to add 4-bit values together. Because I actually built this circuit on a board, I limited the architecture to 4 bits, but there's no reason this couldn't be used to add larger numbers together. The footprint would be much smaller than equivalent parallel adder, but has the drawback of requiring more clock cycles to sum each bit and settle on a valid result. The two 1-bit input values being added together will be called X and Y. The state diagram shows each of the states, as well as the transition between the states. The sum output shows the sum of the two input values as well as the current value stored in the carry, which comes from the previous addition step. The carry from the previous addition is equal to the state assignment. In this manner, you could consider the carry value to be a synchronous or Moore machine type of output. A state table can then be derived. This is a relatively straightforward state table as there are only 2 states. When there's currently no carry, the only way to generate a carry is for X and Y to both be equal to 1. When there's currently a carry, the only way to eliminate it is for x and y to both be equal to 0. Let's use a JK flip-flop to build this. The reset state needs to be the state where the carry is 0, as this brings us to a clean slate with no initial carry values when we start a new set of addition, so this has a value of 0. This state assignment also makes sense in light of the fact that if we want the state assignment to be equal to the carry value, the state assignment must be 0 if there's no carry. The other state, representing a carry, will have a state assignment of 1. The next state expressions are JA equals XY and KA equals X prime Y prime. As mentioned, the asynchronous output will be X, X or Y, X or A, where A is the value of the current flip-flop output. In this video, I have the circuit wired up and go through a few different addition examples. Before each addition sequence, I clear all registers and flip-flops by using a toggle switch to send a low signal to all of the asynchronous clear pins. First, I enter the value 6 and 6 into each register. Then I press a second push button to act as a clock and shift signal to add each bit together. It takes 4 cycles to add the two values together. The second example shows the addition of 5 plus 4. The last example shows the addition of 7 plus 7. This circuit does not contain any kind of overflow detection, as that would not really be relevant to the design of a finite state machine, but it could easily be included in a more robust design of a serial adder circuit. Sometimes there are straightforward reasons why a finite state machine should be designed as a Moore machine or a Mealy machine. These reasons would primarily include the need for a synchronous or asynchronous output signal. However, all other things being equal, what are the pros and cons of each type of circuit? A Moore machine is typically simpler to design, and because outputs are synchronous, there will typically not be any need to worry about glitches or false output signals. On the other hand, a Mealy machine has the benefit of requiring fewer states than an equivalent Moore machine due to the fact that output values can occur on transitions and do not require their own states. However, the asynchronous nature of the output signals may mean the outputs could glitch or have a false reading if timing isn't carefully considered.